Good morning, everyone. So thanks for coming to the IAS Distinguished Lecture. And today we have honor with Professor Khalil AMINE. Okay, I can call Professor now, guys, because he's a visiting professor at our university, the Department of Chemical and Biological Engineering, and also Energy Institute. Okay, so Dr. AMINE actually, old friend of us, and have given several distinguished lectures already. And this time he will stay here about 1 month. Okay, so after lecture, if you want to talk with Carl, you can still book a time with him. Okay, so Dr. AMINE is an Argonne Distinguished Fellow and also the lead of the Advanced Battery Technology team at the Argonne National Laboratory. Okay, he's responsible for all the battery research, related research there. And he's also the deputy director of the U.S.-China Clean Energy Research Center, actually which was established by Professor Xi Jinping and Obama at that time. And he also served as a committee member of the U.S. National Research Council at the U.S. Academy of Science on battery-related technology. He is also a adjunct professor at Stanford University and of course the Hong Kong University of Science and Technology and Peking University. And due to his numerous achievements in battery area, he has received many awards. Okay, I just name a few. He's a recipient of the 2003 Scientific American's Top Worldwide 50 Research Award, 2008 University of Chicago Distinguished Scientist Award, and also 2009 the U.S. Federal Laboratory Award for Excellence in Technology Transfer. He's also the 5-time recipient of the IND 100 Award, which has been considered as an Oscar in the science and technology. Okay. So he's also the award, the ECS Battery Technology Award and the International Battery Association Award. He has published over 500 papers and holds close to 200 patents. Okay, so that's a larger amount of the IP there. Okay, the greater brain. Okay, and he's the one of the most cited scientists in the world from 1998 until 2018. He's one of the highest cited scientists. He serves as president of the International Meeting on Lithium Batteries and also chairman of the International Automotive Lithium Battery Association. And he is also the fellow of the Electrochemical Society and also associate editor of the Nano Energy. He is also a diversity board member of our Energy Institute and also the SIM-based research project, the eFuels, that's led by Professor Tim Zhao. Okay, so actually he is involved a lot in our university. So today he will give a talk on the toward mass electrification of vehicles, role and technology supported by governments and the industry partners. Okay, I'd like to welcome Dr. AMINE to give the lecture.
Thanks. Thank you, Noah, for this nice introduction. It's okay. Yeah, first I would like to apologize for my voice. I'm still recovering from a very bad cold, actually. Not, it was, I had it in Chicago before I came in. So. And I must appreciate Minhua for giving me some good medicine, allow me to stand before you today and talk about, my title is Toward Mass Electrification of Vehicles. What I would like to do is to show you the role of the industrial government, mostly US, China, Germany, and Japan, in trying to set up a vision as well as supporting research on battery technology to enable mass electrification of vehicles. And I will also describe the different technologies that will get us there. Some of the data I've already shown briefly, but some are new that I would like to share with you. So let's start with the first view graph. I like to show this because it clearly shows energy is very important. The humanity top 10 problems for the next 50 years, #1 is energy. It's not water, it's not food or environment. And the reason is because within the next 50 years, the population, world population will reach almost 10 billion, and the demand on energy will double. Most of the actual source of energy is hydrocarbon-based. It's based on coal, petroleum, or natural gas. the renewable energy is still very low. It's almost 8%. And within that 8%, solar, which is ample energy, is only 4%. And there is two reasons. One first reason is there is not a reliable and low cost and safe energy storage that can store this large amount of energy. But also the energy cycle usually take about 50 years to be dominant. This is what I mean. If you look at the year 1800, it was wood, and then the coal come in, and within 50 years, it's basically take over 75% of the energy source. Then oil, then natural gas, because it's cheaper and cleaner. Now the renewable is just right there, it's just started. Now the I believe it will be much more accelerated because of the demand needed for enabling mass electric vehicle. So we'll see it down the road if you want. You can do it the same way here. You can see the renewables are a very small part of the non-transportation, mostly residential, commercial, and industrial. Still, coal, natural gas, and oil are a major player. For transportation, obviously, the only source is oil, and unfortunately, a big chunk of the energy is wasted in heat. So not only we are relying on one source, but we waste half of it. So the situation is very unsustainable. So in the United States, and I think in China, definitely in Hong Kong, at least in the United States, 70% of petroleum is used for transportation. So, and within that, 85% is used for on-road vehicles. In U.S. also, transportation is the second largest expense after housing. So you can imagine if you change the paradigm from oil to electric, I will definitely change the U.S. energy economy significantly. Fortunately, transportation is, electrification is underway. And this is because mostly these two countries are leading. Europe, within 2 years, which is just tomorrow, the European has actually set up a law within 2020. Every car that's been produced must meet 58 miles per gallon. Now, with the, obviously, diesel can meet that, but diesel has been very unpopular. It was a good timing, so many, especially German companies, are actually phasing out a new vehicle based on diesel. China is the average, which is very tricky. The average between conventional and electric must meet 56 miles per gallon, and how they can count for that. But U.S. is much more lagging, and I think our president actually canceled that, unfortunately. But it doesn't matter because most of the U.S. car manufacturers are very much present in Europe and in China. So anything they develop in these countries, they can bring it back to the United States. Electrification also is underway because we have at least 3 major forms of electrification. You have the hybrid. This one has been very popular and the dominant as of today because the battery used is very small, so the cost associated is very limited. So like the Prius, you can buy a Prius for $18,000. The battery is mostly used to assist the main engine and recover the energy in regenerative braking. The other one, which is more of interest, at least in the United States, is the plug-in. This one has a whole range of technologies. You still have an internal combustion engine. You have at least one or two or three, or even 4 electric motors, depending if you have 2-wheel or 4-wheel drive. You still have a very large battery that need to allow you to go to your work and come back all electric. And you have a transmission and a tank. So you can see very crowded technology. So the requirement on energy for battery is very, very severe here. Much more severe than even for full electric. And then you have the full electric. I think in Asia, mostly China, is very popular. Here, the battery is the heart of the vehicle. Large energy battery can allow you to go long electric drive range or can allow you to reduce the cost. So these are the main ones. So I think these are the two that pretty much the focus now for the next generation BEV or PHEV. So this is the global EV forecast that was done by Bloomberg New Energy Finance. Within the next 12 years, you can see the growth is exponential. Within the next 12 years, the expectation is we're going to get at least 20 million vehicles. At the moment, actually, this is very conservative because in 2018, there is about 3.5 million electric vehicles sold. But here, the forecast is only 2 million. So you can see, I expect by 2030, we may have even 30 million electric vehicles. Now, to get there, of course, governments, mostly industrial government, are pouring a lot of money to try to enable low-cost, efficient energy storage. They allow you to go long electric drive range with high efficiency. So the United States, and especially the U.S. Department of Energy, is the main funding agency that actually fund most of the battery. This limited funding from the U.S. Department of Defense and Department of Commerce, but the big chunk of the funding comes from the Department of Energy. And the mission, as is stated here, is to enable market penetration of electric vehicles through innovative battery research and development. So the goal is to implement a technology that can meet at least $100 per kilowatt hour within the next 5 years. And with a fast charge time of 15 minutes. Obviously, the ultimate goal within the 2030 is to get into $80 per kilowatt hour. If you get into these numbers, then you have a cost parity with the ICE engine. So an electric car or a normal car will cost the same. So obviously, it will be the end of the ICE-based technology. Budget-wise, I didn't have the numbers, and I don't want to be misquoting the Department of Energy. So I know that there are hundreds of millions of dollars that's been spent on battery research each year, at least 300 million or more. In 2014, and because of the Obama Recovery Act, the United States spent $4 billion to support battery and material manufacturing. So we do have a base of manufacturing in the United States in anticipation of the growth of electric vehicle down the road. Yeah. So most of the research and development is centered in national lab. There is 17 national labs. I would say 9 of them are involved in research and development. Argonne is by far the leading organization. We have also PNNL, which is running in the Battery 500. This is a new program. It's a $50 million program for 5 years. And also Berkeley is doing a lot of fundamental research. Sandia is mostly doing safety. So each lab has its own niche. We don't do duplication. Also, the Department of Energy is funding many universities and also small companies as well. The agencies that fund the research are the Office of Science. This is the largest office within the Department of Energy. They focus mostly on fundamental research, mostly to understand and predict and control the interaction of matters and energy at the electronic, atomic, and molecular level. J. Caesar, which is the energy hub, is funded by the Office of Science, and Argonne is the leader in this project. It's a $125 million, 5 years project. Also, the Office of Science is funding many EFRCs, that's the Energy Frontier Research Center, with focus on many teams within the battery research. There is at least, to my knowledge, 6 or 7 of those. The second office, which is actually initiated by Obama administration, is the ARPA-E, the Advanced Research Project Agency Energy. This one funds high-risk transformation research that come out of universities or startups, mostly. And then the biggest funding agency is the applied research out of the Vehicle Technology Office. That's the office where I get most of my funding. It's within the energy efficiency and renewable energy. This one has basically the 3 components. It funds basic research and applied research and implementation. So you have full system development and testing, high energy density and high power density cells, extreme fast charging, advanced battery material research, and the battery 500 that I explained to you just before. So within the Office of Vehicle Technology, the 2018 budget was $115 million. So actually, we're talking about it, you know, initially the government wanted to reduce, but the Senate has added more. So it used to be 100, now it's 115 million. So they added 15 million. So the research are based on material. They call it Advanced Battery Material Research. It's a big program that has pretty much all the national lab involved and the universities. And the focus is on the material. So high capacity cathode, enabling lithium metal would give you high energy. High voltage electrolyte for the same reason, to get energy, and solid state electrolyte enabled. So the cell material target are shown here. You can see the anode is moving from carbon to pretty much silicon or lithium metal. The capacity of the cathode has to be above 300 and develop a solid polymer electrolyte that has very high. So once materials are matured in this area, it moves to this section here, which is high energy and high power cell R&D. And in this case now, the criteria is based on a cell, not the material. So we need to do electrode, design, engineering of the electrodes, fabrication of high density cells, diagnostics to understand the issue with this technology at the cell level, and improved manufacturing process. And these are the target. 350 watt-hour per kg. This is within 5 years, and the next 5 years, 750 watt-hour per liter, and these are the cycle life and current life. So once this cell configuration become more mature, then it move into what we call full cell development and testing. This type of work is done in collaboration with the USABC, the United States Advanced Battery Consortium. This is a consortium that made of DOE and the 4 car companies, GM, Ford, Chrysler, and Tesla, and also the grid companies as well. So here, several battery companies are involved, and it is a co-share. So the money I show here comes from DOE, and the industry will co-share 50%. So he's talking about almost a $200 million program. And the focus here is to cost reduction of the technology and doing tremendous amount of testing and validation. As I mentioned, the target is it's actually dropped here, is $100 per kilowatt hour at the pack, $125 per kilowatt hour at the pack level. So this is the effort from all this has led to cumulative U.S. electric vehicle and plug-in of almost 800,000 within the last 5 years. As you can see, it's led by Leaf and Tesla and the Chevy Volt. In 2017, we have almost 200,000 vehicles. It's a growth of 23%, and that's because of the reduction in the cost of the battery and the amount of models available in the market, which is 39. And this expansion of electric vehicle in the United States has led to a gasoline displacement of, at least in 2016, of 140 million gallon. In 2018, is over 200 million gallons. So there is an impact there. Now, this is the United States. I would say China is by far the leading organization in mass electrification. The reason is because of the pollution. I mean, you can just go and see by yourself when you go to Shenzhen in winter or Beijing. The Chinese central government are investing a lot of money, maybe twice as much as the United States, to support local companies, a lot of support and subsidy if you want. And also, some of the money goes to research institution. Now, the advantage of China is the local government also are matching the central government support. So basically, you get twice the money, and that's very important. We are working in Shenzhen. If you get money from the central government, the Shenzhen government basically give you the same amount. So those money goes to incentive for buying electric vehicles, support battery and material supplier, and subsidy for electric car makers. Now, that effort has actually led to 100% electrification of motorcycle in China, which is, and over 20% of electric buses and taxis. Shenzhen City, based on my colleague, and also the mayor that I met last year is leading. And basically, each new bus introduced in the city must be electric. So you can't have a conventional system. So this is a good way of electrifying. The growth is very phenomenal. For example, in 2018 alone, there was 1 million electric vehicles. That's basically more than the cumulative electric vehicle in the 5 years in the United States. Mostly are electric, but also some plug-in and some electric buses. If you look at the China versus the world, by 2017, 2/3 actually of the electric vehicles was made in China. And the distribution is mostly in the north and southeast of China, in big cities like Beijing, Tianjin, Shanghai, Hangzhou, and Shenzhen, for instance. Now, the United States, 5, 6, 7 years ago, actually, the United States and China has come together under the leadership of Obama and Xi Jinping, and they created what we call the U.S.-China Clean Energy Research Center. It's a big center. With a cost share, it's almost $25 million from each side. It's led by Argonne from the U.S. side and Tsinghua University from the China side. And the idea is to create a clean energy consortium. This center is virtual, obviously. It has partners, mostly from the national lab and universities, from the US side as well as from China side. I tried to see if we can have Hong Kong as well, and it doesn't seem to be happening. The center has not only academia, but also industry that co-share 50%. So we have battery companies, auto companies, and I would say utility companies from both US and Chinese side. And it's very visible because of, for example, the review meeting, annual review meeting is attended by the ministers of China most, and also the secretary of the DOE usually. And the focus is on 4 trusts. The largest one is the advanced battery that I basically chair. And there is also vehicle technology, connected and automotive vehicles, and system assessment. Now, so this is about China and US. You know, the other big country that play a major role in advancing electric vehicle and research on battery is Japan. Japan is a leading, and NEDO, which is New Energy Development Organization, is a major funding agency within Japan. Its mission is to address energy and global environmental problems and enhance industrial technology within Japan. Their funding comes mostly from the Ministry of Economic Trade and Industry, and they mostly fund technology development and large demonstration projects like a Green City, for instance. They also fund the industry, universities, and research institutions as well. This is the summary of NEDO's performance target when it comes to energy storage. Within 2030, I would say all the targets within these countries are very similar. By 2030, the energy density must meet 500 watt-hour per kg. It's very similar to the very 500 that the US has set up. By 2030, we have to meet the 500 watt-hour per kg. The cost is almost similar. It's 10,000 yen, which is about maybe $90 per kilowatt-hour. And the driving range is 500 kilometers. This is on the electric vehicle. On a plug-in, by 2020, this is very aggressive. Getting energy density to 200 watt-hour per kg, which is very high, knowing that there are many, many technologies in the plug-in, and a cost of almost $180 per kilowatt-hour. So NEDO is funding many organizations, and 2 of them that stand out is this one. The first one is the Consortium for Lithium Ion Battery Technology and Evaluation Center. They set up this mostly to try to move materials that are developed by material company to the battery. So you can see the members are all chemical companies. So they are developing cathode anode electrolyte. And the idea within this center, they can actually perform and evaluate this material and basically move them to the potential electric car companies like Toyota and Honda and so forth. So the mission, as I said, accelerate commercialization of novel cell component, which contribute to the high performance and high safety and cost reduction. And the other mission, the target is to develop material evaluation techniques that can help these chemical companies by having like a benchmark testing and validation index for not only to battery industry but also academia. It's a long-term project that will last until 2022. So they have several sections. The second big program, which is more of a fundamental program, is RISING. That's the Research and Development Initiative for Scientific Innovation of New Generation Battery. It's out of Kyoto University. It has 13 universities involved, 4 national labs, and 13 companies. Very extensive. It's the largest program within NATO. I think it's about almost $45 million a year. And it's a 7-year project, first phase, and now the second phase, which started last year, is 5 years. So their mission is to clarify basic principle and mechanism of battery reaction using cutting-edge technologies and diagnostics. The idea is by 2030 to demonstrate innovative battery having an energy density of 500 watt-hour/kg, very similar to China and US. As I mentioned, the first 7 years is basically focused on getting 300 watt-hour/kg and develop advanced analytical techniques, which they did. And the next phase is to get into that 500 watt-hour/kg by adding additional improvement. Again, the major focus here is to develop new analytical tools, mostly in operando, so you can interrogate basically the cell during operation. So they've done that using the spring, the advanced photon source that they have is similar, and developing all institute tools using pretty much synchrotron radiation, neutron radiation, NMR, and so on. So this is Japan. So in Europe, I would say Germany is by far the leading European country that is really promoting electric vehicle. And it's obviously there is a reason. They have 3 major car companies, BMW, VW, and Mercedes. And Germany actually is going a little further than US and Japan. And a reason because they come in late. They are actually funding not only research, but also manufacturing equipment. So basically, they want to have everything done in Germany. The manufacturing of batteries, the equipment, the materials, and the battery. So they have many, many programs, as you can see here, toward this purpose, either for know-how, material process and production, and also competence built up by creating a center of excellences. For example, they have a center of excellence for solid-state batteries, for sulfur, for lithium air, and so on, and also post-lithium ion, as I mentioned here. And they do several collaborations. So we are, US and Germany now are in the process of signing an agreement to have similar concept like US-China. So the landscape of research is very wide, as you can see. The advance of Germany, not only the research are funded by the Federal Ministry of Education and Research, but a large number of companies, like BMW has a center of excellence where they funded many renowned scientists around the world. The same thing BASF is doing it, so that the money spent by the industry is far much higher than the government. So very serious. For example, BMW just set up a $240 million research center where they can build actually batteries and then validate them and transfer the technology to the battery companies so they can make them for them, for instance. VW has announced $54 billion production of electric vehicle just a few months ago. So the objective, as I mentioned, is ensure the technology sovereignty because of the car companies that are very known in Germany, development of innovative strength, easy transfer of research result, into industrial application, basically battery made in Germany from scratch. And I think they will do it. And of course, education of highly qualified personnel. And also they're thinking about recycling because they don't have any resources, obviously. And these are the performance targets. For some reason, it does say superior, but their target by 2030 is something in a 400 watt-hour per kg, which is very different. But if you look at the cost, which is very aggressive, it's almost similar. So that would be a challenge. 75 euro, that's almost $80 per kilowatt hour. I don't think so you can make it with this energy density, but it does say superior. Now, all this effort by this government is to reduce cost. And if you reduce costs, you can expand mass electrification in the market. And that's basically what is the main barrier, that millions, hundreds of millions of dollars. Of course, the main target to get in here, to have that parity, as I said, if you really want to reduce costs, you have to increase the energy density. And I did show you pretty much every government is targeting this number here by 2030. So obviously, I think to explain it again, if you use a conventional chemistry, you get very heavy and bulky batteries. If you increase the energy density and reach that 500, you can make the battery smaller, lighter, and therefore compact, and that's a reduction across the board of all material, active and inactive. This is a way to reduce the cost. Of course, the target is to get the same thing as fuel tank, which will be a big challenge. But at least if you can reduce the cost by half, it will be definitely a big impact. So obviously, the only technology that can allow you to do that is lithium ion, because it has the highest volumetric and gravimetric energy density. In another word, you can make it smaller, lighter, and yet very energetic. The technology of today is based on NMC. That's a cathode that was invented at Argonne, actually, and carbon. So these two material has either a lamellar structure where lithium can be intercalated and deintercalated very easily, or a layered structure where lithium can be inserted and deinserted. So because of that, you get thousands of cycles. The next technology will be based on silicon to increase the energy density. The reason, as you can see, silicon has the highest volumetric and gravimetric energy density than any other metals. See, carbon is here, silicon is right there. So if we are able to triple the carbon energy density, that will make a significant impact in getting toward that 500 watt-hour per kg. Unfortunately, when you alloy lithium with silicon, you get a significant increase in volume change. So within few cycles, the particles are cracking and delaminating. So address that, a lot of work has been done in trying to incorporate silicon in carbon matrix to keep conductivity, because once you break up, you have isolation of the particle and they are not participating in the electrochemical process, and that's the reason why you have a quick fade in the capacity during cycling. So these are the works being done by a number of academia, basically incorporating silicon in carbon matrix, either fibers or coaxial sponge or nanotubes. Or I would say it has not been successful industrially because of the costs associated with these processes. At the moment, the companies are just mechanically mixing silicon with large amount of carbon. So there is a lot of work to be done in that area. The electrolyte used in lithium ion is a mix of solvent and salt. So you have either a cyclic carbonate that give you high dielectric constant, or linear carbonate for lower viscosity, so you get high conductivity. The salts are mostly LiPF6 because the other are either explosive, toxic, or have low conductivity because of ion pairing. The problem with the electrolyte is, especially organic solvents are mostly flammable. So even though small cells, I'm not sure if this one works. This is an 18650 based on NCA. If you just nail it, So if you really want to move away from flammability, you have to consider all solid-state batteries. There is an advantage to that because it can allow you to use lithium metal, which has the highest energy density among any other anode. So, and therefore, the amount of lithium you use is very small. So the thickness is, and that can reduce the pack thickness. So basically, by moving from a conventional lithium ion to a solid-state battery, you get a 70% gain volumetric energy density and at least 40% gain on gravimetric energy density. These are very big numbers. And not only you are making a safe battery, but you are also increasing the energy, which means reducing the cost. But there are a lot of problems with this system. I'm going to cite them briefly. Well, let's first see what are the solid electrolyte available so far. So of course, you have polymers, which is a PU base. This one has been actually commercially available now in Ballard, I think, Bolloré. It's an electric car that you can see in Paris, actually. They have about 10,000 of them. It uses a PU, an iron phosphate, and lithium metal. But the focus is mostly on a solid, true solid, either in a form of sulfide, which are very, especially this one here is very popular, or oxide. You have Nazicon, Lizicon, or perovskite and garnite, or nitrite. The Lipon has been commercial for a thin film type battery for smart card, for instance. So there is a whole host of them. Some of them actually have conductivity as high as liquid electrolyte. But they do have several issues. Some of the ion conductor or solid ion conductor like LLZO, for instance, is very sensitive to moisture, so it reacts. So you can't use it. The fact that you're using a solid electrolyte in conjunction with the cathode and anode that swells, they're in charge and discharge, so it starts forming void nucleation. And that's creates interfacial issue. There is also a contact issue with lithium metal, for example, the garnite. But this one has been solved by ALD coating of aluminum oxide. You can see without it, it doesn't have a contact. Contact actually is very, very small. Once you do a kind of ALD coating, you are able to basically immerse the lithium inside the garnite, for instance. And if you do that, then you start thinking about the chemical instability. The reaction with lithium metal is an issue that leads to growth of interfaces that create a large interfacial impedance. And then, even though all this, you still have the dendrite issue because through the grain boundaries, lithium can basically sneak in, within this. And I have a video, I couldn't find it, where you can see lithium actually moving through the solid state from one side to the other and creating a short. So it's not, you really have to have a glass, zero pinhole, or no grain boundaries. Those are the challenges of solid state battery. Now come back to the lithium ion and the cathode. I didn't mention that, but I think I should, yeah. These are the two critical materials for EV batteries at the moment. It's cobalt in the cathode and lithium. The reason why cobalt, because the amount of cobalt reserve is far much lower than nickel or manganese and so on. There's already 13 million tons available worldwide. And cobalt play a big role as a cathode. The other problem is the child labor. Most of it come from Congo. Congo is a very unstable country. There's a lot of war, civil war. And the mining is basically child. So that caused an issue with the Europeans and the Americans and so on. So this is an issue that eventually when the electric vehicle expansion grows significantly, you will have an issue with the cobalt. The lithium is mostly centered in South America, in Chile and Argentina and Bolivia. The cost of lithium actually has tripled in the last 5 years because there are more demand. So you can imagine when you're talking about 30 million vehicles, it will be an issue. And that maybe has led to considering either nickel-rich or cobalt less, or basically zero cobalt. So when you go nickel-rich, the nickel is very reactive. And so we develop at Argonne a full gradient material where we put the nickel, we bury the nickel in the center, and then we reduce it going into the outer layer like this. That's one approach that actually now being licensed by at least 4 companies, big companies, and maybe that's one possible. You can actually design your cobalt to be in the critical area where you need to be. It doesn't have to go all the way from the center, the berg to center. If it's effective in the surface, then you can put it only in the surface. So we talk about 1% or so. And we actually, through industrial collaboration, we built a large cell. These are 18650 cells that shows the NMC that the industry is targeting for next generation electric vehicle is 811. So they put 10% cobalt here. At room temperature, this is the performance because you have high concentration of nickel that is highly reactive. So the performance at high voltage goes down fairly rapidly. Remember, the target cycle life is 1,000. So you lose almost 35% after 300 cycle. The FCG that I show you that is scalable, this is a 600-ton scalable full gradient with a partner. It shows far much better performance because we minimize the nickel at the surface. Even at high temperature, it's much better than at room temperature with the conventional one. That's one way of doing it because this material, to be honest with you, even now we remove cobalt, we start worrying about nickel also. That's the next step because there is maybe 20 times more reserve of nickel, but manganese and iron are in 1,000 times more. So that's where we should be. And that brings me to the next step, which is basically shifting to sodium ion. Now, sodium is shown here. So it's on the crust of the Earth. It's about a little, I would say like 4% or 5% versus 12 ppm when it comes to lithium. If you take the sodium carbonate, it's $150 per ton. The lithium carbonate is $7,000 per ton. And there are less of it, so eventually it's an issue. The sodium ion concept is very similar to lithium ion. So you have a carbon, or disordered carbon, amorphous carbon if you want, as anode, and you have a layered oxide as cathode, so you shuttle sodium between the cathode and anode. Pretty much similar. So the difference is in the sodium ion, unlike in the lithium ion, you have many phases that can form. So you have either an O-type phase where the sodium is in the octahedral phase. In this case, it's the average oxidation of the metal is 3+, which is a fully sodiated phase. But the problem is this phase has multi-step reaction during charge and discharge. This is not good for electric vehicle because the control of state of charge becomes a challenge in this case. The other phase, which is the P phase, where the sodium is in a prismatic configuration, if you want. Here, the material has much high diffusion coefficient, so you can have high rate of moving sodium in and out. And also, the stability of the structure is much better than the O phase. So most of the people are trying to develop P-type phases. Unfortunately, the amount of sodium in these P-type phases is very low, less than 1. So you shuttle less sodium, which means your energy is low. So that's the issue. People have tried actually to do sacrificial salt. It's taking this phase and adding some salt to it as an additional amount of sodium if you want. And here's an example. You take a material and you put a salt like sodium carbonate. And then when you start charging, this is what happens. You have a gas, CO2 gas that comes, so you create sodium and holes in addition to the material, the composite you have. My colleague Theo from CIC has developed a fairly benign sacrificial salt, which is sodium carbonate, that is easy to manipulate. Other has looked at phosphate or nitrate that are either explosive or flammable. So this is one way of increasing the energy while maintaining the robust structure and cyclability of this material. Now, here are the number of cathodes that has been developed in the past 5 years. You can see there's quite a bit of them. And you can see, for example, some of them has no cobalt or nickel. It's basically manganese, iron, and titanium, which are in large reserve. So the advantage of sodium is not only allow you to replace lithium with sodium, but also allow you to get very abundant transition metal in this case. Here is an example of manganese iron based. So once you start doping this material, you can see the polarization become low, and also the cyclability is better. Also the rate capability is better. This is just an example, for instance. Now the challenge with sodium is the anode. There are not too many anodes, unlike lithium, where it can intercalate easily in graphite. Sodium cannot. So there are a whole bunch of potential anode. A lot of them doesn't work. But the one that we are working on at the moment that shows a lot of promise is phosphorus. Phosphorus can give you a theoretical capacity of 2,600, which is very large, similar to the silicon. The problem is when you sodiate phosphorus, you have almost 450% expansion in volume, similar to silicon. So that leads to pulverization of the particle or delamination, as you can see here. So what we're doing at Argonne is trying to engineer electrodes that has phosphorus in a nano phase, and we have kitchen black as a conductive matrix, and multi-wall carbon nanotube that can give us, that can connect the nanoparticle of phosphorus. In this case, we can use very high loading of phosphorus, for instance. This is how we start with very big chunk of particle. We basically ball mill them, and we end up with very uniform distribution of carbon and phosphorus in the electrode. You can see it's almost similar to lithium. It has actually better efficiency than silicon. The average voltage is about 0.4 or 0.5. The efficiency almost 100% after the first cycle. And depending on the rate you use, you get very high capacities, almost 2,000 here. If you increase the rate, you go to about 1,800. And this is show you performance going even much higher in rate. You get close to 1,000. So this is a very interesting anode for sodium. So if you start cycling, you initially start with an amorphous phase because you do ball milling, and then when you end up at the end of the discharge, you form a crystalline phase, which is basically an I3P, for instance. And then when you start charging, it becomes amorphous again. We confirm that also by in situ TM. You can see at 0.8 volt is amorphous. This is electron diffraction. And then when you get into the full discharge, you get a crystalline phase where you can see the patterns. And then go back on charge, become amorphous again. And we put in a full cell based on this cathode and black phosphorus. You can see it cycled fairly well, and it has very high rate capability as well. So now black phosphorus, you know, phosphorus has three phases. It has a white phosphorus, which is very explosive. You don't touch that. You have the black phosphorus, which is expensive, but it's very conductive. And then we have red phosphorus, is dirt cheap. So we looked at actually trying to reduce the cost by going to red phosphorus or a blend of red phosphorus. And here is an example that shows actually red phosphorus also works very well when you blend it in small quantity with black phosphorus to allow you to get conductivity. Because red phosphorus is insulating, you get actually very good performance as well. So this is an example of enabling a very high energy density sodium base by actually taking advantage of high capacity of the anode. Now, if you look at the technology trend of what I showed you, using what we call a techno-economic modeling that we develop actually at Argonne. This is an open source, so you can actually go to Argonne and download it. And so the technology of silicon is around here. But if you look at the sulfur, we are way down. Actually, we're close to 100, which is the target for the next 5 years. Now, sulfur is basically dirt cheap. It's about $120 a ton. People will give it to you for free at the moment. But it's a 2-electron transfer, has very large capacity. Gravimetrically is far much higher. It's almost 10 times that of any cathode known at the moment. Volumetrically is very similar to lithium ion. This is an example where we have a cell that has 3 times more energy than lithium ion, for instance. But the sulfur has several challenges. The first one is the conductivity. It's very insulating, very low conductivity. So you have to put a lot of carbon in the electrode configuration. And if you do that, you add a lot of inactive material, which is carbon, and that defeats the purpose because your energy will drop. The second problem is the swelling. When you move from sulfur to Li2S, you have an 80% expansion in volume. And that can lead to cracking and delamination. And because of that, most of the researchers, they use very low mass loading of sulfur, which also defeat the purpose because the energy at the cell will be much, much less. Perhaps the challenging problem is the shuttle effect or the dissolution of polysulfide. That's something that not been addressed. Basically, during the discharge, you have a low chain polysulfide that dissolve in the electrolyte and then basically stays at the anode. And then you have the challenge of lithium metal dendrite because you're using lithium metal. So you can see it's very, very complicated. So as far as the conductivity, I would say like 90% of the publication that I've seen on sulfur is impregnating sulfur in carbon matrix. Because sulfur can melt at about 110 degrees. So you melt it and you put it in different porous carbon. So you have either macroporous or mesoporous, macro and micro. And that's pretty much a big chunk of the work. Obviously, it does work. So when people have shown some improvement, but it does not affect the delamination because of the expansion or the dendrite or the shuttle effect. So at Argonne, we've been looking at this system here, selenium sulfur. It's a new material. It's no more sulfur. This selenium sulfur has conductivity which is 20 order of magnitude than sulfur. So the conductivity issue is already gone. You don't need to melt it in carbon if you want. It does have very similar volumetric energy density than sulfur. Gravimetric is still lower, it's half if you want. And of course, you can use selenium because it's expensive. It's $70 a kilogram. So you have a whole phase diagram. And of course, the target here is to get as much sulfur as you can. Here, the cost of this material is about $200 per ton. So it's still far much cheaper than any cathode material in lithium ion. And you can see through Raman, you get different signature, which means you have two materials. It's not just a mechanical mix. So we've been working on this material, and we developed this. The electrolyte, I think we are about to publish it. It's actually an ether, a fluorinated ether that we used. So when we use it, you see the voltage profile is totally different from a conventional sulfur-based, where you have steps that are basically indication of a polysulfide dissolution. Here we have one main reduction peak. There is no dissolution, at least initially in the naked eye, comparing to ether-based. But if you really want to be clear about dissolution, we develop a new technique where we use in situ Xanis. Xanis, you basically can check the oxidation state of anything in an amorphous phase or crystalline phase or even in a liquid phase, like in the electrolyte. So here, these are thousands of Xanis spectra. They're in charge and discharge. So you have to deconvolute all this data. If you have a reduction that is happening, which is a sign of polysulfide dissolution, you should have a kind of deviation toward low energy because your oxidation state change. But if you don't have that, it means you don't have any dissolution. And that's what we've seen here. It's like a flat. There is no dissolution. They're in charge and discharge with this new electrolyte. And here, the configuration is 70% selenium sulfur in the electrode. And when you do DQDV, you can see there are multi-reduction peak because of the polysulfide dissolution. Here we have one main reduction peak only. Also did some DFT calculation to calculate the solvation energy of this polysulfide or polyselenosulfide in HFE. That's what it is, that's the electrolyte. And you can see the energetic of this new electrolyte is much higher. So it's very difficult to solvate and dissolve. And these are initial data. We're still optimizing the system. You can see with this new high concentration of sulfur in this configuration, we get far much better result both at 1C and 2C rate. In this case, the load-in is about 8 milligram per square centimeter, which is very high comparing what people are putting together. Now, if you really want to take care of the cracking and expansion that I said, the best way, or also the dendrite, I think the best way is start with the lithiated phase. Instead of starting with sulfur, you start with Li2S. So if you have Li2S, the electrodes already expand. So it will contract. So it's easy to control. But the most important, because you have lithium, you don't need lithium metal as anode. So you can use, for example, silicon, which is much more less, I would say, challenging than lithium metal. So you can see we can hit two birds with one stone. So the problem with Li2S is also insulating. You cannot melt it in carbon. Yeah, you go to 900 Q, you decompose it, so you cannot. So we have to figure out a way, how can we incorporate Li2S in a carbon matrix? And we figure out a way just by basically forming CS2. CS2, it's a gas. So you take, for example, a coke, carbon coke, very cheap, and you react it with sulfur, and you form CS2 gas. So basically, all the sulfur is taken away. So if there is any impurity in the mine, it stays. And then you react this gas with lithium, and for some reason, we end up with actually Li2S caged in graphene cage. You see, we're able to demonstrate that the Li2S is inside this graphene cage by electron diffraction, by X-ray, and by Raman, as you can see here. Because of this, we can put very large loading, truly. Most of at least the university, put about 0.5 to 1 milligram per square centimeter. So you can put 10 in this case, as you can see. And what happened is that there is a contraction and expansion of Li2S within the graphene cage during charge and discharge. So this is one example of course, getting rid of both the dendrite issue by completely eliminating lithium, since you are starting with the lithiated phase, and also taking care of the expansion and delamination. Okay, so to finish, if we go back to the projected cost of different technology, you can see that the best technology is the lithium oxygen, and more specifically, a closed system. You basically reach that $80 per kilowatt hour. So it's a holy grail of all batteries. That's where you can go. Okay, so this is how lithium air work. You have lithium ion here, you have lithium air here. Basically, the configuration is very different. It has lithium metal as anode, an electrolyte, and a porous carbon with a catalyst. So oxygen come in, lithium come in, and you form Li2E, which is lithium peroxide. This is very highly energetic reaction. So in another word, so basically use air while driving and release oxygen while being charged. So it can be better with the system. And this is a schematic of how the system works. So initially you have a first electron transfer to form lithium superoxide, and then the second electron transfer to form lithium peroxide during the discharge process. And then during the charge, you dissociate the lithium oxygen bond one by one. Yeah. This is more challenging reaction, actually. The reason because lithium peroxide is very resistive. So if you go back and look at the challenges of lithium air, there are many. You can see the polarization is very high. The lithium peroxide that you form basically oxidize the electrolyte and decompose it. There is a potential of oxygen crossover and basically showing up all the lithium metal. And also the lithium peroxide that is formed within the pores are not soluble in the electrolyte. So basically they clog the pores, so you don't have any more fuel coming in, if you want. So these are some of the challenges. But if you go back and look at the schematic different reaction, so as I mentioned, the first electron transfer can give you a superoxide radical, which is very oxidative. They can react with the electrolyte. If not, it will react with lithium and form lithium superoxide. And you have two paths. You have a disproportionation reaction that people has been basically mentioning all along, or this lithium superoxide react with lithium to form lithium peroxide. So this is what we are targeting. You can see there is no oxygen, so it can be a closed system. This is very energetic reaction if we can stabilize the lithium superoxide. So most of the people that report mostly amorphous lithium superoxide, it tends to disproportionate almost immediately. So it's very unstable. So that's what we start looking at. We develop an electrode configuration which is based on reduced graphene oxide, and we put in nanophase iridium as a catalyst. And we noticed during the initial discharge, polarization drops significantly. Remember, without catalyst, we have a charge potential at about 4.5 volt. But with this new catalyst, the polarization dropped to 3.4 volt, for example. And it cycled very well, entered the lithium metal because of crossover. The lithium metal died. So once we change the lithium metal, it continues cycling. So that was interesting. So the first thing we want to know is the morphology of this discharge product. Because if it's a lithium peroxide, it's like donut shape, as we call it. But we find out through SEM that we have a nano rods, which is totally different. And also, the rods are on the top of the catalyst. We did some Raman, and we find out that we have indeed a lithium superoxide in the system. These are basically lithium superoxide, not peroxide. And we did also some hard X-rays that we can see that. Because we've seen signature of lithium superoxide, even at 7 days aging, which tell me there is stabilization here, because it doesn't exist, lithium superoxide. So we have to calculate the spectra, basically. The fact that we've seen a signature means that we have a crystalline phase, not an amorphous phase, which tend to disproportionate. So that was good news. The next step is to try to confirm more by using DEMS. DEMS can allow you to determine the electron transfer, how many electrons. And we're able to do that, and we have only one electron transfer in this case. So that was a clear evidence that we have a superoxide phase. Then we try to understand what happened, why it stabilized. So we did some TM, and we find out that the iridium catalyst has actually changed, react with lithium and form iridium-3 lithium. Yeah. And if you look at the structure of this material, actually there is a lattice match between the lithium superoxide and this new catalyst. So it's like the superoxide is capped on the catalyst. And this is the reason why we've seen those rods on the top of the catalyst. And my friend Larry has actually did some DFT calculation to look at the if there is any disproportionation happening with this crystalline phase. And the answer is not, because the energetic are very high. And it's get even higher in the presence of the electrolyte. So all this indicate that we could actually stabilize. So the question now is, can we get that as a starting material and see if it can work? And the answer is, well, we did another experiment, sorry. How much time? I think I should stop, huh? Yeah, okay. So here is another way before we got the DIMS, just to show you the energetic of this reaction. So when we discharge, we got superoxide, and then we discharge in air. There is no oxygen, but yet we get another, we get another discharge curve. If there is a peroxide here, we should say nothing. Huh? So clearly, so what happened is that this is the first reaction. You form a lithium superoxide, and then the fact that you don't have oxygen, the second reaction is basically react with lithium in a closed system, and you form lithium peroxide. So if you go back and look at the energetic of these two reactions, you can see they're very high, 1100 and 2000. And if you go further with a 3-electron transfer, you can get even much higher. So in this case, if you are able to activate only 40%, you get 500 watt-hour per kg that we are targeting in lithium ion within the next 12 years. And if you get to this level, now we're talking about 25%. If you activate only 25% of this reaction, you achieve that 500 here. We're talking about like less than 10%, which is achievable. Huh? So we did a demo. So we made some crystalline superoxide in a large quantity of cobalt oxide catalyst. We were able to cycle the material for 200 cycles at 2.6 volt. This is the NMR that shows that you start with a superoxide and start forming peroxide. So my conclusion, electrification of vehicles is underway with slow growth, but it's going to expand exponentially within the next 12 years. I need to reduce costs. That's a key word. And I would say governments across the world, especially US, Europe, Japan, and China, and Korea to some extent, are aggressively supporting electric vehicle commercialization and expansion. Thank you.
Oh, thank you very much for a very nice talk with a lot of updated information. Now, you mentioned that one aspect is about the use of lithium metal. Do you think that even you get a perfect solid electrolyte, dendrite formation is still a problem?
Yeah, I would say the dendrite will, lithium will grow in if there is like grain boundaries or pinholes. Yeah. But if you have a glass, for example, that's maybe a solution. The glass you don't have is zero pinhole and there is no grain boundaries. So that's an opportunity there. So obviously you have to think about the contact between the glass and the lithium metal. You have to look at how glass is stability with lithium metal. Is it stable or not? These are all things. But you still have to be honest with you, because you have one solid that does not change the volume, and then you have the electrode that change volume both. You may want to put another gel, expandable gel, between the solid and the electrode to prevent this interfacial issue. So these are things that people are considering.
I just wonder, realistically, in about 5 years, if one look at the commercial product available, among all these technology you mentioned today, which one will win out in about 5 years, both in the safety consideration and energy consideration? So it would be practical to put on the electrical vehicle roughly at that time, about 5 year time frame.
Sure. Good question. I think the target for 5 years is 350 watt-hour per kg. At the moment, I think Tesla is about 265 watt-hour per kg using the 18650 configuration. So the next technology they're going to see will be a nickel-rich, 80% metal, transition metal in the cathode with less cobalt, maybe 10% cobalt. As I mentioned, that's what the auto industry is aggressively developing. That can give you about 210 milliampere per gram, which is about 30% higher than the existing technology now. And very likely you'll see silicon introduction in a small quantities in a 10 to 15%. So a combination of these two with additive to stabilize the interface will be the next 5 years that the industry is targeting now. So there is no major big changes. No, it's more of an incremental. The solid-state electrolyte is just in the research stage. It's going to take more than that to be in the market here.
Thank you very much for the very information talk. So Argonne National Lab actually holds a lot of patents about lithium-rich material, but you didn't mention about this material for the further development. So would you please share some opinions on this?
Now the Argonne patents the formulation is very broad. It includes NMC as well that is used. The lithium-rich has the advantage. It's manganese lithium-rich, so which is will address the issue of cost because the cobalt and nickel concentration is very low. And the capacity of the material is very high. It's about 260 milliampere per gram, which is higher than most of these nickel-rich based. Of course, there is an issue with the, which is intrinsic to the structure, which is voltage fading. So maybe in consumer electronic, maybe it's not a major issue, but for electric vehicle, once your voltage minimum drop below a certain value, you are dead. So because of that, it cannot be used in electric vehicle at the moment. It's still under trying to. We understand the issue is a transformation to the spinel. That's why you get the 3 volt, and it is very difficult to. The spinel happen when you activate the system initially at 4.6 volt. So one potential solution is to stop before the activation. But your capacity drop to 200, which is still attractive in regard that you don't have much nickel and cobalt. So that's something that we can look at. Yeah.
Okay. Any more questions? Okay. So there's no more question. Next, thank Dr. Khalil AMINE again for the very nice talk.